Now that we've had a chance to look at the three basic passive components, let's summarize what we've found and have a look at resistors, capacitors and inductors in AC circuits as a comparison. Firstly, the resistor dissipates energy as heat and opposes the flow of current at all frequencies. The capacitor doesn't dissipate energy, it returns it to the source. It holds the energy as an electric charge on its plates. I leads V in the capacitor by 90 degrees, but the most important thing about it is that its reactance decreases with frequency. So the higher the frequency, the less and less it opposes the flow of current. The inductor in many ways is just the opposite. It's a coil of wire and it stores energy within its magnetic field. V leads I by 90 degrees in the inductor, and this time the reactance, the opposition to the flow of the current, increases with frequency. One of the most important applications of all these components in AC circuits is in filters. These are circuits which cut out certain frequencies or let certain frequencies pass through, and we will be discussing this in a couple of videos' time. One final area which we need to cover before we leave them is how they add up in series and in parallel. Resistors in series just add up together. So if we have three of them, as shown in the diagram, the total resistance is just R1 plus R2 plus R3. This means that if we don't have a suitable size of resistor for a particular application, either because we don't have it or because we want to make up a certain precise value, we could just add up smaller resistors together like this to make up the value that we want. Inductors in series add up in exactly the same way as resistors, as shown in the diagram. The odd one out is capacitors. When we add capacitors in series together, they add in a rather peculiar way. 1 over the total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now let's turn to the components in parallel. If we add resistors in parallel to each other, they add up exactly the same way as the capacitors did in series. That is, 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This results in the total resistance being less than the smallest resistor that we have in parallel. For example, if we connected two 1K resistors together in parallel, we'd get half a K. Inductors follow the pattern set by resistors. They add up in parallel in exactly the same way, as shown in the diagram. Finally, we have capacitors in parallel. And again, they break the rule. They add up in the same way as resistors and inductors did in series. The total capacitance is equal to C1 plus C2 plus C3. And a consequence of this is that if we wanted to make up a new value of capacitor by adding several smaller ones together, we would add them up in parallel, not in series.